2 seconds. Fix my screen. 2 seconds. Window protector. Okay. Move around a bit. See, what am I teaching today? Oh, we're gonna teach you how to scam people. Okay, Keith, you're gonna be my accomplice. I'm gonna send you a secret message. 2 seconds. We're gonna scam people together. 2 seconds. Okay, Keith, I sent you a message on Discord. It's a secret thing. So read that, and we're gonna scam people together. I need some accomplish. Okay. Wait, why didn't I put it here? Okay, so today we're gonna learn something called, you can hear me, right? Because I switched a whole bunch of devices today. Let me check. You can hear me just fine, right? Except I don't know where the chat window is. Ah, 2 seconds. The resolution is so bad. 2 seconds. Let me help you with that. I switch my screen and everything looks funny. Okay. Okay, so today we're gonna learn something called expected value. Okay, but before we do that, we're gonna scam people together with Keith. So I need one volunteer to get scammed. Anyone? Actually, I need two. I need to. Okay, so we're gonna play a simple game, Justin. Actually, this game is scamming people, but there's a chance that you're gonna get scammed instead. There is a tiny chance. Okay, there's a Justin and there's Keith because you know he is my accomplice. Okay, there's Keith and Adan PD. Okay, I sent him some message. I sent him some scamming message. He probably never realized what exactly it means yet, but he's gonna do exactly what I said. Okay, we're gonna play a simple game. This game is called Head or Tail, right? This is very easy to understand. And since Pongshai cries, so Pongshai, you're gonna be the judge, okay? With the judge called. Do you have a nickname though, Pongshai? Do you have a nickname? Okay, Bomb. Bomb gonna be the judge. Just a second. Bomb gonna be the judge. By the judge, I mean you need to toss a coin. You need to toss a coin. So the game is simple. So Justin gonna call either head or tail, right? Okay, he's gonna call head or tail. I don't know. Let's make it look like this. We're gonna call head or tail, and then Bomb gonna toss a coin. Okay, and tossing a coin, so it's either come head or tail, right? So here's how the payout works. Let's say everyone bet 2 baht. Okay, you need to bet 2 baht. You need to bet equal amount. Actually, the scam work either way, but let's make sure that the number come out nice. Okay, everyone gonna bet 2 baht. And what's gonna happen? That means the total pool is 6 baht, right? So if it comes out head, what happened is that all the winners, okay, in this case, there are 2 winners, they're Justin and Ajahn Piti. Okay, Justin and Ajahn Piti gonna split the pool. Okay, split the pool. That means what's gonna happen is that Ajahn Piti gonna get 3 baht and Justin gonna get 3 baht. Okay, so that's the total profit. So Justin gonna be +1, Ajahn Piti gonna be +1, but Keith gonna lose 2. Is someone good with the game? The game is very simple. You bet 2 baht, right? And okay, you bet 2 baht each turn, and if you're right, you split the pool among all the winners. Like it, there's also a case where if everyone is wrong, then you split the pool either way. But you get the idea. Is everyone good? Any question about the rule? We're gonna play it like 10 turns or 20 turns, 15 turns. Okay, Bomb, be a judge, be a good judge though. So let me write this. So there's also Justin, there is Keith, and there's Ajahn. Okay, and there's a judge called Bomb. Okay, so for each one of them, I'm gonna split it in half. So there is, okay, so this would be the bet, and this would be the profit, and this could be what they bid on, and this is the profit, bet and profit. And Bomb is going to be whatever the coin toss. Bomb, do you have a coin? Bomb, do you have a coin? Did you find a coin? Yes. Okay. So before Bomb throw a coin, okay. Bomb, don't cheat with Justin behind the scene though, please don't. Okay. So here's gonna be what happened. Justin, tell me head or tail? Head or tail? Head. Okay. Justin head. Keith, tell me head or tail? Head or tail? You would say head. Okay. So let me bet tail. Okay. Bomb. What was the coin? Tails. See? So let's look at the payout, right? The pool is 6 baht. The total pool is 6 baht, right? There's only one winner. That means I'm getting all the 6 baht, but I bet 2 baht. So the profit here is +4 minus 2 minus 2. Is everyone good? Is everyone good? Right? There's only one winner in this case. Okay. So Justin, again, I'm gonna let you bet. What's the number? Head or tail? Head. Okay, you like head so much. Keith, tell me, what do you like? You like head too? Okay, so I'm gonna bet tail. Okay, Bomb, your turn. Did you cheat? You don't get extra point though for letting me win the game. Okay, next one. Turn on your camera. He doesn't trust you anymore. Mom, can you help him? Unless you're in like unless you're naked, then unless you're naked. Well, some of you are in pajamas, I'm pretty sure. Because that's what I do if I turn off the camera too. Okay, so let's do this. Okay, so let me bet first. Let me bet first because I bet tail so many times already. Let me bet head. Keith, what do you bet? Keith. Tail. Justin. Head or tail? Head. Sure. Mom, help me. Unless you have camera. Head this time. Okay. So that's a head. Okay. So that means here's what happens, right? There is 6 baht. There are 2 winners. So each one of them get 3 baht and 3 baht. Are we good? Right? That means Justin +1, Adapity +1, but Keith gonna be -2. He's down by so many. Okay, so this turn, Keith, tell me first, what are you gonna bet? Tail, Adapity gonna bet head, and Justin. Head, you like head so much. Mom, help me. Let's play this for like 10 turns and then you're gonna see. Tail, so it's a tail. So that means gonna be +4, -2, -2. Are we good? Right? Let's play it 6 more turns. Okay, let's do this quick. Justin, tell me. Justin, okay, Justin changed his mind. Keith? Tail. Okay, let me bet head. Okay, Bob, help me. I think I scammed you just a little bit, but Justin, you're just unlucky. You are not expected to lose this much. You're not expected to lose this much. Just trust him. Did he turn on the camera though? I don't know. Okay, let's do it like 3 more turns. Let's do how many? 5 already. Let's do it 8 turns. 8 turns should be enough to see what happens. Okay, Justin, tell me. Head. Keith, tell me. Keith, head. Okay. So bomb, help me. This one. What is it? Head. Okay. So it's gonna be -2 +1 +1. Okay. So bomb said head. Okay. So Justin, tell me. Head. Keith. What is it? Keith, head. And bomb, help me. Bomb say head, right? So it is going to be what? +1 +1 -2. Okay. +1 -2. And 1, 2, 3, 4, 5, 6, 7. Okay, last turn. Justin, this is your last turn. One last head. Yes. Keith, what is it? Your tail. That's okay. I'm gonna. Bomb, tell me. Tail. So that's gonna be +4 -2 -2. Okay, so let's tally up. Let's tally up. This game seems fair, right? Everyone thinks it's fair, but I sent Keith a secret message earlier. Okay, so the total, let's do the total. So -2, -10, +7, -7. Okay, and -6, -8, -6, 8, blah, blah, blah. So Keith is 0. So Adapity +7. Okay, interesting. Is this actually guaranteed that Justin will lose? That Justin will lose. It's sort of guaranteed with a really high probability. We're gonna talk about that. But anyone see how Adapity and Keith, what is Adapity and Keith doing though? Well, what are we doing? Why do we say that we cheat? Okay, so Justin noticed something. Justin noticed something that, okay, Adapity and Keith, they always bet the opposite. But it's a fair game, right? We split the pot at the end. We split the pot at the end. What's the problem with betting the opposite to each other? What's the problem? What else did you notice? What else did you notice? What else did you notice? I think you should notice something. Yes, one of us will always win, but that's for sure. Did you notice something about the payout? Do you notice something about the payout? Yeah, they have to add up to 0. Okay, that's one thing. What do you notice about the payout, especially for Justin? What? Anyone notice the payout, especially for Justin? For Justin. Right. Can you be more specific though? So what is missing? What never happened for Justin? What never happened for Justin? Right. If you notice, right? Adapity and Keith sometimes they get +4 and then we get a huge profit. We get, right? But for Justin, he can only get +1. He never have +4. Why is it? Can you tell me why is it though? Why is it that Justin never have +4? Anyone knows? Why is it that Justin never have +4? Right, because whenever Keith win, right? Whenever Keith win, it's either Ajahn Piti or Keith gonna split the pot with him. That means Justin will never win alone, right? So notice the following: never win alone. Okay. Just notice here. If he bet it right, think about this: never win alone. So there's no +4, right? If you think about Justin, right? What is the probability that he's going to be correct? If you look at Justin only, what's the probability that he's going to be correct? A half. That's clear to everyone, right? That's probably a half. He wins. And that's probably a half if he loses. Right? If he wins, how much does he get? I think I draw the tree somewhere. Where is it? Oh, I draw a tree in the lecture notes. If he wins, how much does he gain? +1. If he loses, how much does he lose? -2. Now, can anyone tell me how much does Justin is expected to lose each turn? Right, that's a secret message I sent Keith at the beginning. All I tell him, right? All I tell him is, please bet the opposite of what I do. Wait. Can anyone tell me? Like I never define what the word expected mean. But can you tell me how much does Justin is expected to lose each turn? 1 -1. How would you calculate it though? How would you calculate it? I never defined it. We're gonna define later, but I want your intuition. If you have 0.5 probability of winning, and very good. So we're gonna add both up, but we're gonna multiply by the associated probabilities, right? So expected, let's say Justin profit. Okay, right? He has probability a half of winning 1 baht. And he has probability a half of losing 2 baht. So that means each turn, how much does he expect to lose? Add both up, gonna be -1/2, not +1/2, -1/2. So each turn, Justin is expected to lose 50 stan, right? Sound good? You can now see, right? How is this a scam? But you never know. It's not very obvious at the beginning. That just a simple message I sent Justin, just a simple message I sent Keith at the earlier, right? Really to Justin getting scammed so bad because the game seems fair. We split the pot and so on. Is everyone good? Don't get scammed by something silly as this one. And I think if you try to make a business out of this, it's gonna work. So for example, Okay, I'm not gonna tell you. I'm gonna tell you later when I turn off the thing. when I turn off the recording, there is something on the internet right now that clearly is a scam. Okay, but everyone can see, right? If I draw you this diagram, you know right away that Justin clearly gets scammed. Okay, in your homework, you're gonna do this in the case of 4 people. In the case of 4 people, you can scam that person even more than we scam Justin. Okay. Any questions so far though? Any questions so far? The story I said in the homework was true though. When I made that problem, there was one girl. She is now an epidemiologist who came in the class late, so she didn't get to see the trick. It was a true story back then that she came in class late, so I made that homework for her. Okay. Any questions though? Any questions though? Everyone can clearly see, right, that this is clearly a scam. Any questions so far though? Any questions so far? Yeah. So let's define expected value. Okay, let's define expected value. So let's define expected value. Okay, so expected value right? Like we did last time. Okay, like we did last time, it is the mean. It is the mean of the random variable because Justin profit is a random variable, right? It's based on the outcome, which you can actually draw the tree. The lecture note has a tree, and you're gonna need that tree for your homework. Okay, so go read the lecture notes for the tree. It's a really big tree. Okay, so far so good. So let me define expected value. Expected value is, so for example, expected value, I typically write like this, double E. Sometimes if I'm lazy, I'm just gonna write one E. Expected value of a random variable, let's call that R. Okay, is going to be the sum over all the outcome of R omega times P of omega. Okay, so far so good. It just means that, okay, for each outcome, just calculate the probability. Just calculate the random variable. Okay, and then just multiply them, sum them up together. So you get essentially the mean. Sometimes you call this the mean. It has a really nice property, which we're gonna learn later. Okay, so let's do the following. Okay, let's do example. You get the intuition on what it does. Okay, example, let's say a fair six-sided dice. Okay, let's call it the face of the dice. What is the expected value of D, where D is the face of the dice? How would you calculate it? How would you calculate it? Very good. So it's going to be 1/6, right? That probability times 1. Oops. Let me write it the other way. 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6. It seems like the job for Python, right? Times 1/6. But you know how to calculate it. You're going to get essentially it's 3.5. Okay. Everyone get? Okay. That's how you calculate expected value. You just multiply the omega, the R omega. This thing is R omega. This thing is P of omega. Right? You're going to get 3/2. And one very important fact that you should notice that 3/2, you never roll a 6-sided dice and it comes up 3/2, right? Unless you're like really cheating with the dice. Okay, this is never not in the range of random variable. Okay, so that means the expected value may never really come up in the output, but it's the mean of all the random variable. Okay, any questions so far? Or any questions so far? Okay, but you may ask, Ajahn, but what you just calculate is not exactly this formula, right? What we just calculated over here, the fact that Justin's gonna lose half a baht every turn. Okay, it's not exactly this formula, right? Because I did not do the omega and such. Okay, that's another way to calculate it. It's like exactly the same way. So alternative way of calculating expected value. Okay. So for example, instead of summing over the instead of summing over all the omega, so we said this before, right? That E of R is the sum over all the outcome of R omega times probability of omega. Okay, this is good, but sometimes it's annoying. So for example, there are many outcomes that leads to Justin winning. Okay, so for example, there are many outcomes that leads to Justin winning. For example, if Justin bet head and Ajahn bet head and tail and then bomb. So this is Justin, this is Keith, and this is Ajahn, and this is bomb, right? This is how Justin wins. Justin could win it like this: head, tail. Ajahn could get head, and bomb could be tail, and so on. And I could switch Keith and Ajahn and so on. So there are many outcomes that give you exactly the same, that give you exactly the same random variable, right? Okay, so far so good. So when that happens, right? You're gonna know that okay, Ajahn, there's a lot of terms that give you 1. There's a lot of terms that give you -2. So we're gonna group them by the random variable of that outcome. So let me convince you that this is exactly the same thing as x in range of R and then multiply by x times probability that R is equal to x. Okay, this is exactly what we did before. Exactly what we did before, right? So we said that, okay, Ajahn, I'm gonna multiply that x is 1 and -2, minus plus 1 and -2, right? And the probability of each of them is 1/2. Okay. Right, this is exactly what we did. It's the same thing. So whichever one is more convenient, so you just pick it. Okay. Any questions so far though? Any questions so far? So this is more or less a definition. Okay, this is more or less a definition. This requires some proof, but the proof is in lecture note. It's 3 lines. You can do it. You just, I think I convinced you. You essentially just group the terms. Okay, you essentially just group the terms. Any questions so far though? Any questions so far? I just tell you the definition. Expected value is used in a lot in quantums and statistics and probability. Used a lot, even though it's like the worst metric you can do. We're gonna look at that later. It's not the best metric, but it's the easiest one to calculate for sure. It's the easiest one. It has all the nice properties. Okay, so let's do something fun, and then we're gonna calculate something amazing. We're gonna calculate something really amazing together. Okay, so now let's look at the following. I claim the following: if the random variable is always a positive integer. Okay, if r is always a positive integer, so that means if you try to calculate the expected value, right, you would do the following, because you just sum up all the positive integer. You could sum up from I equal to 0, doesn't matter, I, and probably r equals to I. Okay, you could sum up from 1, doesn't matter, or 0. Are we good? Right? You would do this, except this thing is actually can be really hard to calculate. The probability that it's I equal to I sometimes is really hard to calculate. You're going to see later. I claim the following. Let's get my claim first. I claim that this is equivalent to expected value of R is also the same thing as sum of I equal to 0 to infinity of the probability that R is greater than I. Is it 0 or 1? 0, 0, 0. Okay, good. This is really is 0. Okay, so I want to point out, can you see the difference between the two, right? The first one requires that you know exactly how much the thing gonna happen for each one of them. The second one is required that you know that it's gonna survive more than certain values. Okay, and the proof may not be so obvious. Let me show you, because it may not be so obvious for you to figure out in 5 minutes. Okay, so let's look at this. The probability that R is greater than 0, right? Probability that R is greater than 0 is going to be the probability that R is equal to 1 plus the probability that R is equal to 2. And this is true only if this thing is always a positive integer. Okay, that means you cannot get 0 plus the probability that R is equal to 3 plus the probability that R is equal to 4 plus dot dot dot. Okay, and let me write the next one. Probability that R is greater than 1 is going to be the probability that R is equal to 2 plus the probability that R is equal to 3 plus the probability that R is equal to 4. Okay, and I can do one more. R is greater than 2 is going to be probability that R is equal to 3 plus the probability that R is equal to 4. Okay, so that's good. So the term that we add up here are from here. Okay, are from there. And I claim that if you add this thing up, okay, if I add this thing up, okay, so a probability of R greater than I from I equals 0 to infinity. Okay, let me ask you simple question. How many of this term are there? If I add them up, how many are there? How many are there? 1. So it's going to be probably. So let me write 1 as well. 1 multiplied by probability that R is equal to 1. Plus, how many of these terms are there? Going to be 2. So plus 2 times probability that R is equal to 2. And I think you convinced, right, that this thing is 3 times probability that R is equal to 3 and plus 4 probability that R is equal to 4 and so on. Right? So if you add up to infinity, you can see that you're going to get exactly that guy. Okay, you're going to get exactly that guy. So let me draw like this. Okay, so there are many ways for you to calculate expected value. If it is a positive integer, then this is what you can do. And this is actually quite convenient. I'm going to show you an example right after this. Okay, this is actually similar to the sum that we showed earlier, right? You remember the board, right? You can actually sum it 2 ways and get it to equal. Any questions so far though? We haven't used it, but any questions so far on the derivation and so on? Right. So we just add the probability. This should be amazing, right? This should be amazing because we just add the probability and we get the expected value. We never multiply it by I. So I just claim that these two sum are equal if R is a positive integer. These two sum are going to be equal if R is a positive integer always. So let's look at what kind of random variable that is always a positive integer. Okay, this is very important. This is a very important concept. This is a very important concept. It shows up a lot. This is called mean time to failure or before failure or between failure. Depends on that B has like many meanings. Okay, so imagine the following. So imagine the following. When you buy a light bulb, right? When you buy a light bulb, this is a very important one. When you buy a light bulb, okay, typically the light bulb they claim some number, right? Like, okay, this light bulb gonna last 20,000 hours. You probably heard that number before. You can actually read the box. Actually, let me show you the MTBF. There are many names for this number. MTBF light bulb. There's a there's also a box. Let me find out your box. No. No. Can't find the box. But you probably see this before in the spec sheet. It requires this. Even when you buy a hard drive, like you ask, what is the expected failure time for the hard drive? Then you're going to say, okay, 2 years, 5 years, and so on, depending on the brand and depending on what you buy. Okay. What do you think? How exactly do they get this number? Okay. Think about this. The light bulb came out on day 1, right? The light bulb came out on day 1 and they say it's going to last 5 years. Did they turn on the light bulb for 5 years and wait? What do you think? That's kind of silly, right? That's kind of silly if you do that, right? Why would you wait for it? Right? Why would you wait for it? So this thing typically, so they must measure it somehow. Okay. Let's think about this. Let's say this thing about 20,000 hours. Right? The one that lasts 20,000, I think it's the fluorescent one, CFL one, lasts 20,000. LED lasts like almost forever. The thing that failed first are the power supply, not the LED. Okay, so let's think about this. What exactly does 2,000 hour, 20,000 hour means? Okay. Okay. What exactly does 20,000 hour? That doesn't mean that if you use it for 19999.99999 or something, and then the next second is gonna fail right away. Does it mean that? What do you think? No, right? Because that they're probably gonna get sued, right? Think about this: your computer, if it lasts 3 years, and there's a program in the computer that say if the date equals this one, we're gonna turn off. It sounds very silly to do, right? No one can notice. Not illegal. So you have to buy a new computer. They call premature obsolescence or something. There's a lawsuit. There's a lawsuit. If you search that one, planned obsolescence or something. Planned obsolescence, ESCNSE or something. Maybe, but think about this. Okay, so now you know that each light bulb, right? Each light bulb, when you go by each light bulb. So if this one is a light bulb, right? Each light bulb are not gonna end at exactly the same time. This guy gonna end at 18,000, right? This guy gonna end maybe okay at 10,000. This is a bad light bulb. This guy lasts forever, like 50,000, right? This guy may last like 100,000. Okay, this could be 1,000. And so on. Okay, so these are the random variable, right? Depending on the light bulb you get, you don't know what you're gonna get. Okay, you don't know what you're gonna get, but you get some number, right? So that's good. So that's good, right? So you can calculate the expected value if you want, right? You can calculate expected value if you like. Okay, you can calculate expected value if you like. So you count how many of them gonna fail at this hour, how many of them gonna end at 100,000, how many of them gonna end at 1,000, right? And then you take the average, like what we did. Okay, that's gonna be exactly the mean time before failure. Okay, but that's think about practical way to do this. This is like cumbersome. You need a whole bunch of light bulb, right? Now the problem is that not only that you need to wait 5 years, you need like 10,000 light bulb, and then you need to wait for 5 years. Okay, that's not going to be what happened, even though they're going to probably have 10,000 light bulbs, but they're not going to wait for 5 years. 10,000 light bulb is nothing on the scale of everything, on the scale of if you are a light bulb factory. Okay, so here's what we do. Here's what we do. We're going to model this. Okay, we're going to model this, the light bulb. We're going to model this. Okay, so the popular model, there are many ways to model this. There is actually a term called failure engineer. It means that the engineer that actually do all the math about when the thing gonna get fail and how it's gonna fail. It doesn't mean that this engineer sucks and he fails. Okay, that's actually an actual job. I think it's called failure analysis or something. Okay, this they pay a lot though. I did some project with my client to calculate how long things gonna last. Okay, so here's what we do. The easiest model to do is to do the following. Let's say you have 1,800 days, right? Okay, that's easy, done. Okay, 1,800 days, and each day, okay, and each day you're gonna do a coin toss. Okay, you're gonna do a coin toss each day. Head, survive or fail, or maybe head or tail. Survive or fail. Okay, each day you're gonna toss a coin, survive or fail. If it survives, that means it goes to the next day, and then you toss a coin again. Whenever you hit fail, then that's the end of the lifetime. So if this thing survive, and then this fail. So that means you use it for 4 times, and then you survive. Are we good? Okay, so this thing lasts 4 days, for example. Okay, and this model, right, just like life, that's actually, if you look at this curve, it's almost like the life. That's actually how they calculate the life expectancy and so on as well. They do something a lot more complicated, but they model it behind the scene. Okay, so we're gonna do something even simpler. So this is not true. This is not true because we don't consider wear and tear. Let's say each day you toss exactly the same coin. So that means if you survive the first day, it's like the next day the light bulb gonna look pristine new. Even though you survive for 10,000 times, then the light bulb gonna look pristine fit new. Okay. So the probability that it is going to survive is, let me make sure that I match selection note 2 seconds. Let me make sure I match selection note on the notation. Okay, P is here. Okay, to make sure. Okay, let's say each day you have some probability P of dying. Okay, and I want to know how long you're gonna last. Okay, like just like Squid Game, you have probability P of getting to the next round. Okay. Of course, when we look at this, right, there are going to be people who last 10,000 days depending on P. If you get really lucky. Are we good? Okay. What I am interested in is the relation between this guy. Okay. The relation between this guy and mean time before failure and the number 20,000. Okay. There has to be some relation, right? Because you toss coin every day. If your coin is a half, you're going to last like 2 days. Right? If your coin P, if that P is like 1 in 1,000, you're probably going to last about 1,000 days. Are we good? We're going to find exactly what the formula is, the relation between P and the number 20,000. Okay, any questions though? Any question? Okay, we're going to do that together. Okay, so the random variable that we are trying to find, right, is the life, is this 18,000, right? So we are trying to find the expected value of the number of days survive. Okay. Could we calculate human lifespan? So human lifespan doesn't work like this because if you age like 80s, right? If you are like really old, your body doesn't function the same way when you're young. But you could use it, but it's not going to be exactly correct. You need to correct for it. You need to change the P as you get old. Okay, so this one assumes that if you survive 100 years, you're not going to be like newborn, right? You're not going to be like fresh out of the box. It can be so amazing, like how strong the child are. They tolerate so many things. Okay, like when you get old, you're gonna notice you heal a lot slower. Okay, so everyone understand, right? This is your random variable. Okay, this is your random variable. There are some probabilities that you're gonna survive each day. Okay, so that means if you want to calculate the E of the number survive, right? Then you could do the following. You could do the following, right? You could do the sum of the number of days we survive and probability that we're gonna survive that many days, then die. Survive that. Let's call that n. Survive n days, die on n plus 1. Right? That's exactly what we're gonna do, right? Okay. However, this is actually hard. This is actually hard to calculate. You actually get the sum that you need to take the derivative and so on. For expected value, why is the left bracket missing? Is it a special symbol? Expected value, when I type in the notes, what did you write in P? Let's call this die on n plus 1 day. Let's say exactly. No, my parents doesn't even graduate from high school. But they're smarter than me, so I can tell you, my dad is like super smart, but he can never explain a thing. My dad is super smart, but when I try to listen to his explanation, it's like, this is not a good explanation. Okay, so guys, you get to see, right? Expected number of days you survive. You're gonna do this, which you could calculate it. You could, but I'm gonna tell you, don't. is hard. We're gonna do something a lot simpler. Okay, a lot simpler. You could calculate it. It's gonna come out with the sum that you need to take the derivative and then sum this. It's cumbersome, trust me. Or you need to sum it twice and so on. There's so many tricks to do it. Okay, so what we're gonna do is the following. Notice, we learned something, right? That if the random variable is positive integer, the number of days you survive, because I chop up the time step already, right? Because I chop up the time step already, you either survive 1 day, you either survive 2 days, 3 days, you never survive 3.5 days, right? By the methodology that I did, if you're not happy with it, then you could divide the time even finer, right? So for example, if this thing is a day, if you want, okay, I need 1 hour, then just multiply the 4, just multiply 24. Then you're gonna be happy. But you need to modify the P a little bit as well. Okay. So we know that the number of days we survive, right, is going to be a positive integer, which means we can use the following formula, right? I equals to 1, not 1, 0 to infinity, right? Of the probability that the number of days survive, okay, that the number of days survive is greater than, strictly greater than I. Okay, so far so good, right? This is what we use it, because number of days you survive is going to look like this. Okay, any questions so far? Any questions so far? We use exactly this fact that we learned. We use exactly this fact, right? We use exactly this fact. This is why I bothered to teach you that there is an equivalent. Otherwise, you need to do this sum. Otherwise, you're going to need to do this sum, which is a pain. Trust me, that P doesn't look too nice. Well, it looks nicer, but the sum is a pain. It looks nice, but the sum is a pain. Okay, so let's look at this. That means we need to calculate something, right? We need to calculate the probability that you're gonna survive more than 0 days, right? Plus the probability that you're gonna survive more than 1 day, right? Plus probability survive more than 2 days, and so on. Okay, so far so good. Plus dot dot dot. Okay, so can someone tell me, given our model, how we toss the coin every day, how do you make sure that you survive more than 0 days? How do you make sure you survive more than 0 days? Not a half. You're close, but not a half. So you have probability P of fail and 1 minus P for survive. Right. So that means just make sure that you don't die on day 1. Make sure that you don't die on arrival. Are we good? Make sure that you don't die on arrival. So probability that you're gonna survive more than 0, that is exactly what? 1 minus P. Is everyone good? Right? Just make sure that you don't die on day 1. That's all that you need to do. What about probability survive more than 1 day? Actually, let me add. Answer me first. What's the probability that you're going to survive more than 1 day? Don't die on day 2, right? So it's going to be 1 minus P and then square plus 1 minus P and then cube plus dot dot dot. Does this one sound familiar though? Does this thing sound familiar? Aha. Does this thing look familiar though? What is it? Taylor. I don't remember. Taylor Swift. Okay, good. Okay, I know you all just make a joke out of me. So let me just copy this. This is the geometric series that we saw before, right? Okay, this is a geometric series. Typically, the formula will come out nicer if you count the day it fails as well. If you count the day it fails as well, but oh well. If you're off by one day, then I'm happy. Okay, so let's look at this. Let's look at this. Let's look at this. So all we need to do, right, is to sum this thing up. So let's sum this thing up. Do you guys remember how to do it? You guys remember how to do it? Ring 1 over p, divide by 1 over p. You love to make my life so much harder, but sure. We're gonna divide. Yes, I would multiply, but since Nawat say divide, I'm gonna divide. I would have multiply, right? It's 1 plus q. I think this goes without saying, right? I think this goes without saying. I think this goes without saying because we did it like 10 times. So q over 1 minus p is 1 plus q. Okay. So that means all you need to do is solve for q, right? So we need to do a little bit of algebra, which makes sure I don't screw up. There's a chance I screw up. Q1 over 1 minus p minus 1 equals 1. And then I need to make sure that I did not screw up. So q, and then 1 minus 1 plus p over 1 minus p is 1. Gone. Right? So the thing becomes q is 1 minus p over p. Did I screw up the sign? I did not. Okay, good. So it's 1 over p minus 1. So that is the expected value, right? This is the expected value of the number of days survive. Okay. At least you know it's on the order of 1 over p, the number of days you survive. Sound good? But I'm going to cheat a little bit here because otherwise I'm not going to match the lecture note and the rest of the world. Okay. Because the rest of the world, they count the day that you fail. Any questions so far though about the algebra and so on? Any questions so far before I explain it? Any questions so far? Any questions so far? No. Okay. Typically, what they do, this you don't survive 4 days. You actually survive 5 days. They count the day that it failed. They claim that it fails at the end of the day. They claim that it failed at the end of the day. So what people typically do, they call MTBF, right? It's expected number of days you survive plus 1. So that means it's going to be 1 over p. Okay, so this guy plus 1. This is what people do, but if you're off by 1, then I sort of understand what you're doing. If you're off by 1 day, I kind of know what you're doing. Okay. Any questions so far though? Think about this. It kind of makes sense if you think about it. It kind of makes sense. If you have a chance of failing 1 in 1,000, okay, so you would expect to toss the coin 1,000 times and then you should see 1, right? You should see 1 fail. Kind of makes sense. If it's a half, then you probably take you mostly 2 turns, right, until you get the fail, but then you count the fail as well. 7 good? Seven good? Seven good? Any questions so far? Any questions so far? Any questions so far? So let's do something about life. Let's do something about life. Wait, why plus one? Because we did not count the day it failed. At the very beginning, we did not count the number the day it failed. Right? Now we count the day it failed, so we add one to it. Okay? Now we count the day it failed. Are we good, Keith? Right? So the number of days we survived, that was 4, but people actually count it as 5 because they count the day it fails as well. Kind of like a scam, right? But if you're off by 1, then I'm good. I don't mind because it depends on the definition on how you count the days and so on. Okay, so let me ask you something really simple. This thing actually is a common interview question. Okay, so let's think about this. If you want a baby girl, let's say you're gonna have kids, and you want a baby girl. Actually, this is like totally opposite to China, right? They want baby girl, they want a boy, they don't want a girl. That's why there are like such an imbalance in China. Okay, let's say you want a baby girl. The question is, right now you don't have any kids. The question is, how many kids do you expect it to have before you get the baby girl? Right, including the baby girl. How many kids do you expect to have? So for example, you have baby girl, then you stop having kids anymore. What do you think? What do you think? What do you think? How many kids do you expect it to have until you have baby girl, and then you probably stop having kids? Okay, Bomb said 3 kids before the boy. You want the girl, though. You want the girl. 1.5 kids. Okay, that's not bad. 3 kids, and then the government will stop you. They cancel that. They cancel the one-child policy already. They cancel the one-child policy way back then. I think it's your generation. I think it's exactly your generation. They have one-child policy in China, such that you can only have 1 kid, except if you have a lot of money. Then you can have as many kids as you like. Okay, so let's think about it. Let's think about this. This is like coin toss, right? You're gonna toss a toy. I don't want to say girl is a failure, but you're gonna toss a coin until it comes up the girl, right? So each time you have a kid, right, you essentially toss a boy and a girl, and each one has like 0.5. Each one has like 0.5. And then I ask you, how many turns are you expected to toss the coin until you get the girl? Can you tell me? Right? The real question is, can you turn this problem into another problem which you know how to solve? So how many turns do you expect to toss the coin until you get a girl? How many? Anyone? Not 3, not 1.5. No. It was -1 and then I +1, so it becomes only 1 OP. You know what? So 2. Yes, you expected to have 2 kids, right? Kind of makes sense if you think about the intuition, right? But does that mean 2 kids guaranteed to have a baby girl? No, clearly, because some of you are like 2 brothers already, right? Some people are going to have infinite number of kids and they are all going to be baby girls. Are we good? Any questions about number 2? Any question about number 2? So that's 1 over P. So that's 1/2. So that's 2. Okay, so far so good. Any questions so far though? Any questions so far? Right, we're just applying what we have just proved. Now let me turn the question a little bit harder, a little bit harder. Now, you don't want just the baby girl, right? Now you don't just want the baby girl. Now what you want is at least one boy and at least one girl. So one of each sex, right? At least one boy and at least one girl, and then you're gonna stop having kids. So if you want at least one boy plus one girl, let's say each baby has exactly one sex. Right, there are some people who have the gene for two sex. It's rare, though. I think it's 1 in a million. I think it's 1 in a million or 10 million. It's really, really rare. Okay, let's ignore that case. Okay, if you want at least one boy and one girl, right? So for example, if the first kid is a boy, the second kid is a girl, then you stop. If it's a boy, then a boy, then you wait until you get a girl, and then you stop there. Or if you have a girl first, then you're gonna wait for a boy, then you're gonna stop there. The question is, how many kids do you expect it to have until you have one of each sex? What do you think? What do you think? What do you think? Two? Let's double. 1, 2, 1 over p squared. Can you turn this problem into the previous problem? Okay, that's the real trick for this one. Can you turn it? Right, each child has half a chance of being a boy or a girl. Can you turn this problem? This thing is actually a recurrent, which I think Ajahn Kanat would force you to do one of the problem that is a recurrent. I'm not gonna have you do it. It's annoying. What would you do though? What would you do? Think about physically what would happen, right? You're gonna have one baby first. You're gonna have one baby first. It could come out a boy or a girl. Then what? So how many? Can you tell me how many? It's always one half. No what? It's always one half. P is always one half for getting the boy or a girl. Turn P in no. So let's think about this. What you're gonna do, right? The first baby, it could be a boy or a girl, and then after you have the first baby, all you need to do is wait for a girl, wait for a boy. So the question is, how many kids until you get a girl? How many kids? How many more kids until you get another girl? Two. This thing is two as well, right? By the same reason. Is someone with me though? If you have the first kid, doesn't matter what sex it is, what sex he or she is, right? Then you need to wait for the two to get the opposite sex to complete the I don't know the set. So that means how many do you expect it to get? Like collect them all, right? So how many do you expect to get? Six? No. You have the first kid and you wait for two more. So it's gonna be three, guys. Three. Right? You have the first kid, and to get the specific sex, you need to wait for two, so it's gonna be three. At least you tell me like 12 or something. Why three? Because after you have the first kid, if it's a boy, you're gonna do the game again until you get a girl, and you know that you expect it to play the game 2 turns to get a girl. So it is going to be boy plus two. That's three. Okay, so a lot of problem, right? If you can turn, you can actually calculate the probability. You can actually list out the cases and calculate the expected value. Yes, you can, but it's going to be really annoying. Okay, but if you can turn your problem into the problem that you know how to solve, then that's like a lot better way to do it. Okay. Any questions so far though? Any questions so far? We're gonna take 10 minutes break. Okay, and we're gonna come back. 1522. Assignment question 1 is a stick and stone. I think that's a hint. It's stick and stone. It's a stick and stone. Think about carefully, like what is a yo-yo? What is a candies and what is a student? What did we do in class? Sushi, right? What is a sushi and what is a chopstick? Think about carefully. It's a stick and stone. Is the video I'm sharing like sharp? Because I see some blur on my screen though. Is it like sharp or do you see any difference? The screen that I share? No? Okay, good. I think my screen is too much brightness. How is it zero brightness? Zero brightness on my screen is scary. I don't know, they dropped the class maybe? There should be 30 people because I create like 60 set of exam. Did your webcam turn into a potato? It was good before, right? Because I usually use iPhone camera. Now I try to use the webcam that comes with the screen and it sucks, but I'm too lazy to change it now. Is there a solution for the midterm we had? No, I'm too lazy to do it, but you can ask your friend on how to do it. Or I could just steal one of the student answer. There are some people who get like full score, or at least like I have seen one that get at least the almost full score, like 99. Sometimes you should get 100, but then I feel like you should learn something. So I make a nitpick. So I make a nitpick, make it 99 because if I write 100, then you're probably not going to look inside. So I make it 99 so that at least you look inside. Guys, one thing though, make sure that the score I put on the first page and the score inside matches. There is a chance canvas. So I create the latter part first, and then I put the score on the first page and the last zero on the last problem. could be a problem because when I write it down, Canvas may not save it yet before I go to the next guy. So please check the last zero for problem 6. If you get 10, even though you should get 100, tell me immediately. Which week is this? This is week 9 or week 10? What lecture number is this, by the way? 18, 19, 17, 17? I'm guessing. Okay, so that means we are on schedule on finishing the class. We are on schedule. We I think we might finish the class earlier than usual, which is good. The thing is, we do not have holiday this term, so that's good. So, so Airbus, the webcam is really bad, right? When it comes to your screen, it used to be like much better, right? Okay, I'm gonna switch back to the usual camera next time, but I need to find a spot. Just loaded 2 seconds ago. I want to fix the camera too. Where's my camera stand? Where is the camera stand? I don't know where I put it. I really don't know where I put it. I don't know where my phone is either. May I open the solution for pass homework 6? Yes. Let me do that right away. Do that right away. 1, 2, 3, done. I don't know. I didn't add up the score. I didn't add up the score, but again, like I said, it's a stupid measure. Grade is a stupid measure. As long as you learn something, maybe you write something wrong, but you understood it correctly, then don't bother. As long as you pass, then you should be happy. Yes, I plan to do it that way. Okay, so let's continue on what we are trying to do. Okay, so what we're gonna do in 17 minutes, I'm gonna introduce you to one of the most important concepts, but we're gonna continue on this next time as well. So this is called linearity of expectation. Okay, so let me ask you something important. Okay, let's say I have two dice. I have two dice. Two dice. I'm gonna call it D1 and D2. I never tell you anything about dice. I ask you, what is the expected value of D1 plus D2? What that means that you take the face of the dice, you add them together. What do you expect to get? What do you expect to get? Without any proof, without any proof. What do you expect it to get? We're gonna prove it, but give me your intuition. What do you expect it to get? Ah, you give me the number, but no, it's not 7, right? Kind of 7, actually it's 7. So you expect it to get E of D1 plus E of D2, right? We're gonna prove exactly this property. Yeah, so far so good. This is called linearity of expectation. So that means expected value of the sum, right? E of the sum is the sum of expected value. So that's good. We're gonna prove exactly this property. Okay, I'm gonna prove it by definition. Okay, let me make it more mathematics like. Let me call it R1 and R2. We're gonna come back to the dice later. Let me call this R1 and R2. So let R1 and R2 be random variables. R dot V dot, this thing is random variables. Okay, and then I'm gonna prove that the left and the right are equal. So we can do that very easily, right? So by definition, expected value of R1 plus R2 is the sum over all the outcome of R1 omega plus R2 omega, and then multiply by the probability of the omega, right? So we get the outcome, we calculate the random variable, we multiply them together, and then we add up overall the outcome. This is what we do. And then what we can do is we can just expand it. Okay. For this one, I'm going to write you a proof because I want to point you out one thing. Because I want to point out one very important point. And the left is expected value of R1 and the right is expected value of R2. And we get what we get. Okay. Is everyone good? Right? We are proving the following. Right? It's very easy proof. you just do it by definition, right? By definition, and then you expand, and then you do by definition. This thing is by definition. Okay. The most important question that I want you to ask you, if you look at this proof, did I assume anything about R1 and R2? So for example, did I tell you, did I assume the fact that R1 and R2 needs to be independent? So for example, if you toss two dice, did I tell you that I did not tape the two dice together? If I tape the two dice, what's going to happen by taping? I'm going to explain that later, but I do something with the dice so that the face doesn't really come out like independently. Did I assume? Alexi said yes. Why did I assume? Where did I assume independence? We never assume, right? The thing is, we never assume independent. And let me make a note here. This is very important. R1 and R2, not necessarily independent. Right? If you look in the proof, we never assume that R1 and R2 are independent at all. Okay, I'm going to explain that physically later, but we never use the condition for independent. So this is true. This is why we love expected value so much, because there's a property of expected value that works regardless of the relation between the two. That work regardless of the relation between the two. This is a very powerful fact, and in the homework, the last problem gonna confuse you. Not the last problem for this homework, but the next homework gonna confuse you by a lot, and you're gonna need to use this fact. Okay. So this is why it is so powerful, because it did not assume anything at all about R1 and R2. It's straight from the definition. The fact that you can just add the random variable and it is going to be the expected value of the random variable. The sum of expected value is expected value of the sum. This is a very powerful fact, and it has no assumption now. It's straight from the definition. Okay, so far so good. And then you may ask, okay, Ajahn, let's go back to the die. To illustrate this point. If D1 and D2, right? If you toss two dice, they're independent. You toss a die two times. Yes, you can tell me, Ajahn, that's 7. But what if dice number 2 is electronically linked to dice number 1? That's how you scam people, right? Is electronically linked to dice number 1, such that if dice number 1 is, I don't know, D, this thing is going to be, I don't know, D plus 2, and then mod 7, mod 6, not mod 7, plus 1. Right, so that means you shift it by 1. So for example, if dice number 2 is 4, if D is 4, this thing gonna come out 6 every time, right? If this thing is 5, this thing gonna come out 1, right? If this thing is 3, this thing gonna come out what? I add 2, right? Gonna come out 5. So far so good. If it come out 6, it's gonna come out 2. If it come out what? 1 and 2, it's gonna come 3 and 4. So that's good. So if D1 and D2 are electronically linked by this formula, I just show you the formula, right? If D1 and D2 are electronically linked by some electronics, okay? So that means if D1 comes out 4, D2 gonna come out 6 every single time, no matter how many times you toss D2, as long as D1 is 4. Okay, it's like remote control. It's like a remote control dice, but depending on whatever the outcome is for D1. Are we good? Okay. Now I ask you, what is the expected value for this cheated dice? Right? Now D1 and D2 clearly are not independent anymore, because they actually exist though. Because D1 and D2 are not independent anymore, right? Everyone can see, because if I tell you something about D1, you know exactly what D2 is. That's like the opposite to independent. What do you think the expected value would be? E of D1 plus D2. right? If you trust what we just proved, I said, okay, that's easy. You just add the expected value of dice 1 and dice 2, and each one of them is 3.5. So we expect this to come out to 7. Is everyone good? We expect this to come out to 7. No matter how you cheat it, as long as you didn't change the probabilities, right? Okay, so let's do exactly that. Let's make sure that they come out to 7, right? So this thing add up to 10 and probability is 1/6. This thing add up to 6 and probability is 1/6. This thing is 8 times 1/6. And this thing is 8 times 1/6. This thing is 4 times 1/6. This thing is 6 times 1/6. Are we good? Right? If you add up all these 16, 24, 32, 38, 42. Oh, 6, that's exactly 7. Okay, so the real reason that linearity of expectation is so powerful because you assume so little. You assume so little. Okay. Is that good? No matter how D1 and D2 or how like these two guys are related, it's gonna work. It's gonna work as long as you didn't change the probabilities. Okay. Any questions so far though? Any questions so far? Any questions so far? No, let's do another one. Let's do another one. This is a very important trick that you're gonna need to use. This is a very important trick that you're gonna use. Okay, so let's look at the following. Let's look at the following. Let's say you come in the exam. Let's say we now have an on-site exam. Okay. The first time, right? The first time you do it, the first time that you come into the exam room, I confiscate your phone, right? Because that's what people do. But typically, I don't even bother to check. I confiscate your phone so that you can communicate with anyone. So I take the phone. So if there are 100 students, so I take 100 phones. Then you do the exam, right? Then the exam time. And then at the end, I need to return your phone, but I'm lazy. Okay, I need to return your phone, but I'm lazy. So I'm just gonna return it randomly, right? So for example, if the first guy come, right? If the first guy come, then I'm just gonna pick random from 100 phone. The second guy then I'm gonna pick a random from like 99 phone and so on. Are we good? So of course, not everyone gonna get their phone back, right? Not everyone gonna get their phone back. It sounds silly, but not everyone gonna get their phone back. But I'm asking you the following: what is expected value of the number of people getting the right phone? What do you think? How do we calculate this? If you think about it, they're like, oh, Ajahn, there's a whole lot of combinatoric I need to do, right? Right? The probability that K. So for example, the probability that K people are gonna get the right phone back, then you need to calculate it, right? Then okay, you start thinking, okay, Ajahn, there are K slot, and then you need to count how many going to be correct and how many going to be wrong, and you know that you cannot have like 99 correct and 1 wrong because the leftover phone is going to be that guy and so on. You can see that it's extremely complicated. Like K people get the phone back, even this number is extremely complicated. Okay, I think I convinced everyone, right? The probability that K people are going to get the phone back, that is actually very hard to calculate. Okay, that's exactly very hard to calculate. Okay, because you need to shuffle the phone and then you need to divide by the correct thing and so on. That's extremely hard to calculate. Can we do something easier? Can we do something easier? I think I convinced everyone, right? The probability of getting K people getting the phone back, that's actually quite hard to calculate. You can try. You can try. It's not easy, right? The probably the K people gonna get the phone back because you need to like shuffle 1, 2, 3, 4, 5, and then you count how many of them are in the same slot. You want to make sure that 4 people are in the same slot, and then you need to figure out which 4 are going to be in the correct slot, and then you're going to need to divide that by 5 factorial and so on. It's not that easy. Okay. Right, I quit as well. If I have to calculate this number, I quit. No, we're not going to do MTBF, but close. We're going to do something to make this thing easier, right? Because we know that this guy, even though it doesn't look like a sum, I'm going to write it as a sum. Are we good? Right? Even though the number of people that get the phone back doesn't look like a sum, but if we can write it as a sum, right? If we can write this guy as a sum of something, and that something is easy to calculate, okay? And if that something is easy to calculate, then we're gonna have an easy time to calculate it. Are we good? Right? So the goal is to write this guy as a sum. Because if it is a sum, then we can use this fact, right? That okay, you add the expected value of the sum is the sum of expected value. Okay? So any good idea though? The number of people getting the phone back. Right? Phone back. This is actually a very general trick. What do you think? What do you think? Number of people getting the right phone back as a sum. You may ask, Ajahn, how is this a sum? You just count people. Well, it is, right? It is a sum. If you do the following, let me define a variable. Okay, let me define a variable. I of A, B, C, D, E, F, G, P. Okay, person. Okay, is 1 if person P get the right phone. 0 if not. Okay, is that one good? How is the number of people who get the right phone back a sum though? Let me define the variable. This I actually called indicator random variable. Can you write the number of people getting the right phone back as the sum of something? As a sum of something. Anyone? If you figure this one out, you're gonna remember this for the rest of your life. You know what? Right? It's a sum of I of P. You can think about the indicator random variable as this. After I give everyone the phone, I ask the important question: did you get the right phone back? If you do, raise your hand. So I just count how many hands, right? I just count how many hands at the end. How many people get the right phone back? If you get the right phone back, that indicator variable is 1. You raise your hand. Then I count the number of hands. That's all I do. Right? So it's gonna be sum over all the people. Is someone good on this point? This is a very important point. I want you to see that they are equal. Right? On the right, I just count the number of hands. Right? If you don't raise your hand, then I know you don't get the right phone back, right? If you are 0, then you don't add, you don't contribute to the app. Right. I set 1 to those who meet the condition and 0 for those who don't, and then I add them up together. Then I'm gonna get the number of total people who get the right condition, right? It's like for loop, and then you if, and then you add 1 if it meets the right condition and so on. Are we good? Right. And now you're gonna ask, Ajahn, you just make things more complicated. I say, no. I actually make things a lot simpler. I make things a lot simpler because what we want to calculate, right? What we want to calculate is the expected value of the number of people who get the right phone back, which is the sum over P of I of P. Now you do. Now you know that this thing is expected value of the sum which we can use linearity of expectation to make this guy as the sum of the number of people multiplied by expected value of I of P. Okay, so far so good. So far so good. This thing is linearity of expected value of expectation. If you want to sound smart during the interview, just say this word, linearity of expectation. It's going to make you sound like 20% smarter. On the right question, though, don't just throw this word. In SOP, maybe not. I don't know. They expect everyone who graduates to know. You actually, I saw Risky in the roster. So Risky, I think you've seen this before, right? In quantum, this is what you did in quantum. Expected linearity expectation. Okay. But in this context, it's actually very important because it allows you to calculate something you never know how to calculate before. Okay, so expected value of I of P. Can anyone tell me how much is it? Can you tell me how much is it? Right. So to calculate that, that's easy, right? To calculate expected value of I of P, right? So you just calculate 1 multiply the probability getting the right phone back. Let me just put a check mark and plus 0 multiplied by probability of not getting the phone back. So we can ignore it because you multiply that by 0. Okay. If there are 100 phones that I have, what's the probability that you're going to have the right phone back for each one of you? If there are 100 people, it's going to be 1 over 100. Are we good? So this thing is 1 over 100 because it's 1 times 1 over 100. Expected value of the indicator random variable is very easy to calculate. Yeah, because we just need to calculate that. So that means it's going to be sum over P, which there are 100, right? So I just label them by I of 1 over 100. Can you tell me what is this number? Add 1 over 100 times. Very good. It's 1. Have we get linearity of expectation is so powerful because it allows you to calculate something that you never thought you can calculate before. Especially the trick of turning your variable, especially the count, into the indicator random variable. If you try to count something, typically just turn it into indicator random variable, and then you're good. So far, so good. Any questions so far, though? Any questions so far? Any questions so far, though? Okay. If not, let me ask you a very important question. When we do this, okay, even though I say that, even though I said to you that this thing gonna work regardless whether the random variable inside that you add up is independent or not, it's gonna work regardless. Let me ask you, are all the IPs independent? What do you think? Are they independent? By independent, I really mean the strong one, the mutually independent one. No? Why no? Why no? Can you give me like a very simple example to say why is it a no? Not right. Yes. Okay. So what Nawaz said is correct, but it's the harder counter example. But it's the harder example. So Nawaz said, if you take one phone and if I get the right phone already, the probability that you're gonna get the right phone is gonna be 1 over 99, not 1 over 100 anymore, because there are 99 phones left and one of them is yours, because I took the right phone away. Are we good? So depending on what I get, if I get the right phone, then I know that you probably change for sure, right? Or if 99% already get the right phone, you know the 100% gonna get the 100% gonna get their phone as well. Okay, so far so good. So these I, they are not even, right? They are not independent. These are not independent, but that's okay. But that's okay. When you try to separate as a sum, then you worry, Ajahn, the random variable indicator are not independent of each other. Then don't worry, it works regardless. Okay. Right. Whatever information I tell you about other people should not change your probabilities. Okay, that's the definition of independent. You haven't done the homework, so you probably get sketchy on what exactly I'm saying. But once you do the homework, you're gonna understand it. Okay. Okay. So before we go, there's one more situation that I want to consider. So now I get really creative. 100 people, 100 phone again. But now I'm not gonna give you out randomly. Here's what I'm gonna do. After the exam, I'm gonna have you sit in a circle. Actually, you can do this at a restaurant. I'm gonna have you sit in a circle. Let's say I don't know how many people are there. 1, 2, 3, 4, 5, 6, 7, 8. Let's say there are 100. Okay. And then I'm gonna put your phone in a table. So it's like everyone put their phone in front. Someone put their phone in front. Okay. And there are 100 people put their phone in front. And what I'm gonna do, I'm just gonna spin this guy, right? Because I know that's what you're gonna do. Because you want to screw with people, right? You spin this guy, but don't spin so hard though. The centrifugal force will not be enough to hold it in place and so on. Unless you use super glue, then you can spin it really hard. Right? So if you rotate the table, right, you can see that it's either everyone get the right phone back or no one get the right phone back. Are we good? Right. Seven get? Right? It's either everyone gets the right phone back or no one gets the right phone. Okay. So let me ask you, what is the expected value of the number of people getting the right phone? Let me just put a check mark. Expected number of people who get the right phone back. What do you think? Before you answer, let me ask you one thing to think. Think about what's the probability of this guy. Let's say this guy is Nawat, probably Nawat getting the right phone back, according to this round table strategy. Okay, tell me what's the probability that Nawat gonna get the right phone back if there are 100 people? Still 1/100, right? So now tell me, what is the probability, what is the expected value of the number of people who get the right phone back? Very good. That's still one. This is the beauty of it, right? Or maybe the weakness of it, right? This is a beauty, but it's a weakness of it. Is that one good? It's still one because you go through exactly the same calculation, right? You went through exactly the same calculation. Oh, Ajahn, I want to calculate expected number of who get the right phone back. Then you separate into indicator random variable, and then you get exactly the same thing. Each one of them is 100, and there are 100 people, so you add them up to get one. Right. But if you think about it, like I said, the expected value may never show up on the outcome because the outcome is either 100 or a 0. Okay. So if you calculate this, the expected value of the number of people who get the right phone back, for this one, it's actually easy to calculate, right? You have probability 100 of 100 people getting the right phone back, and you have probability 99 over 100 of no one getting the right phone back. So that's exactly one. These two should match. Okay. Is everyone good? This is why linearity of expectation is so powerful because it allows you to calculate a whole bunch of things. It's a whole bunch of situations. And you know that if you change it, okay, you didn't change anything. Okay. Is everyone good? But I want to point out, let me go over time just a little bit to point out one very important point as well. Okay, one very important point, you can see that this strategy and that strategy and the strategy that I give random people who are totally different, right? The distribution are totally different, but the expected value are the same. So expected value, the weakness of it is that it doesn't tell you about the distribution at all. Okay, it tells you about the mean, but the mean, is not enough to tell you the whole story. It's a good representation, but it doesn't tell you the whole story. Okay, next time we're gonna learn about how to tell more story, but it's not the whole story as well. We're gonna tell more through something called variance. Okay. Any questions so far though? Any questions so far? Okay. If not, we're gonna call it a day, and I think Keith need my live support. Let me turn off the recording. Okay. See you on Thursday.